Hi guys, so today's lecture is going to be about static variables, program memory regions, as well as garbage collection. So I know in the past I've already talked about static variables here or there sort of thing. I know in particular during the midterm review I somewhat covered it extensively, but today's going to be a more formal covering of that material. In terms of memory regions as well as garbage collection, whatever that might be, those can be pretty complex. And so what we're really going to talk about is just a higher level of what's going on. I think the lower level understanding of what's truly going on is somewhat out of the scope of this class. Okay, so we'll go ahead and get started with static variables and what the static keyword is actually doing. So the keyword static indicates a variable is allocated in memory only once during a program's execution. We'll talk about how that might affect your code, or for example, how different objects all reference the same static variable, and what that looks like in a second here. Static variables reside in the program's static memory region and have a global scope. So what is a static memory region? Well, intuitively, it's a region where static variables exist. But we'll actually talk about that in more detail when we get to the program memory regions section of this lecture. So for now, we'll just skip that. And what is global scope? Well, we've already covered this in past lectures, right? The difference between global scope and local scope, and how and I believe I even used static variables for this global scope in Java. But yeah, so global scope means the variables can be accessed anywhere in the program. A static field is a field of the class instead of a field of each class object. And so when I say each class object, I'm talking about an instance of the class, that kind of object. And so what this means is a static field can be accessed without creating an instance of a class. And I believe I've already showed this to you, where you can access a static field just by using the class name and then the dot operator and then the name of the static variable. So let's go ahead and look at an example of this. If we go to the IDE, you'll see I've got a main class with my main method. We'll go ahead and do a print hello world just for good measure to ensure that it works. Hello world. Cool. And we'll run it. Should print hello world. Good. And so where we're really going to start is by creating a class. So we go new, Java class, and we'll just call this my class. My class. And what's going to be in my class? Well, we'll go ahead and make a static variable. Public static. You can't forget the keyword static. That's what is denoting that a variable is static. We'll go ahead and give it a type of int, and we'll call it my static var, and we'll set it equal to 5. So when I talked about a static variable or a static field is a field of the class, and I mentioned that means that I can access this variable just by using the class name. We'll go ahead and look at what that looks like right here. So system.out.println, and what I want to do is print the static variable. So accordingly, my class, I can just use the class name. I don't need an instance of the my class type. Dot my static var. And this is valid. This is valid because the variable is static. Don't know why that did that. So we can go ahead and run this. Let's see how it works. Okay, good. So value is 5, and indeed my static var's value is 5. To show the difference between the static variable and a non-static variable, I'm going to go ahead and create a non-static variable. So we've got public int non-static var is equal to, we'll just do something more drastic, we'll say 10. So a non-static variable is associated with objects, not necessarily the class itself. And so we can see that. First, you cannot access a non-static variable by just using the class name, as is the case with the static variable. And we can see this right here, right? So I can say or what did I call it here? Yeah, non-static var. If I try to type non-static var, it doesn't work. And what is the error? Non-static field, non-static var, cannot be referenced from a static context. And so what is that saying? Well, it's saying what I just talked about, where this variable is not static. Therefore, we can't access it in a static way. But we can access it through an instance of the myClass type. So if we say myClass MC equals new myClass, instead of using the class name here, we use the name of the instance, the variable name, MC, dot non-static var. Well, this is valid, and this should be nothing new to you guys. And so if I call this, right, I'm accessing the non-static variable, and you'll see it prints 10. Interestingly enough, accessing a static variable is not limited like accessing a non-static variable. What I mean by that is I can also access a static variable via an instance of the class. So if I say my static var, this is valid. Now you'll see my IDE has given me a warning. It says static member myClass.myStaticVar accessed via instance reference. Basically what that's saying is, hey, this is a static variable, you should access this statically via just the class name. But you can access it via an instance of the class. That's okay too. And just to prove that this works, I'll go ahead and run it. And you'll see it runs correctly, prints 5. We'll go ahead and, let's see, is that everything I wanted to do here? We'll go ahead and go back to the lecture slides. So, go to the next slide. Static fields can also be called class variables, and non-static fields can be called instance variables. So class variables means that it's a variable tied to a class in terms of just the class name itself. Whereas a non-static field is called an instance variable, which means its memory is tied to each specific object. That's why different objects of the same type, their non-static variables, while they may have the same name, can have different values. A static member method is a class method that is independent of class objects, just like the static field. And so yeah, that brings up a good point, right? You can have static fields, but you can also have static methods. And static methods function very similarly to static fields. They are considered a class method. They're tied to the class name and not tied to each individual object of that class type. Not to say that each individual object of that class type can't use the static method. They can, just like a static field. Yeah, and so static member methods typically are used to access and mutate private static fields. We'll look at that in a second in an example. That'll make a little more sense. Since static methods are independent of class objects, the implicit parameter this, which remember it refers to an object's self, is not passed to a static member method. This means a static member method can only access a class's static fields. So we'll go ahead and look at an example. We're going to go back to my class, and what we'll do is we'll create two methods. One will be a static method, and the other will be a non-static method, doing relatively the same thing. Start with public, the static keyword. The return type will be void. The name will be print static var. No input parameters. And all it's going to do is print the static variable, and we'll say my static var and my static var. There we go. And then we will make a non-static, which is just lacking the static keyword. Same return type, void. Print non-static var. And it will say my non-static var. Non-static var. Cool. So as you can see, the first method is a static method, and it's just printing the static variable. And the second method is a non-static method, and it's printing the non-static variable. So we'll begin with the static method, just to show that you can access it just in the exact same way as a static field. I'm going to say my class dot print static var. And yeah, so you can see the IDE is not giving any red squigglies, it's not giving any errors. This is valid. But let's see if it works. Which it does. And that's what we expected, right? This is what I'm saying where static methods are considered class methods. It's tied to the name of the class as opposed to an individual object. So we have here an individual object. We call that MC. And just to show that you can actually use the individual object to access a static variable. But once again, just like the static field, it's not recommended. It says static member, there's a warning, right? And it says static member my class dot print static var accessed via instance reference. And so you might be wondering, okay, how can this happen if we're saying that the static method is tied to the class name and not the instance name? Well, that's just because your compiler is smart enough to know that you're calling a static method, and really what you meant to do is call it via the class name instead of the instance name. So that's what this warning is basically saying. So we can call it via this. But once again, just like with non-static variables, we cannot statically call a non-static method. So for example, we'll say print a non-static var, and it's giving me an error. It's saying non-static method, print non-static var, cannot be referenced from a static context. And so that's basically just saying, it's a non-static method. You must use an instance of the class instead, because it's an instance method. And so to prove this, we change, instead of using the my class name, we will use an instance of the my class, MC. And there you go, the error goes away. Go ahead and run it to make sure it works. And there it is. My non-static var is 10. And so it works exactly as we would expect it to. So now there are some funky things. The static method can only access static variables. So, for example, if I try to interchange this my static var with non-static var, it throws an error message. It says non-static field, non-static var cannot be referenced from a static context. And so that's just saying, hey, you're using a non-static variable within a static class, and that is not allowed. So we'll go ahead and change it back. But the same is not true for using a static variable within a non-static method. I know it's kind of confusing, but we can show this by replacing the non-static variable with a static one in my non-static method. And this works. Once again, this has to do with your compiler being smart enough to know that you meant to say something like this: my class dot my static var. You just can conveniently get rid of this. And we can show that this works. We'll go ahead and print just normally, as we would, the print non-static var. And it will print it. There you go. And it prints 5. Just as we expect it would. We'll go ahead and change it back. There we go. Non-static var. Okay. I think that's everything I wanted to show you in that example. Go back to the slides. Static method. Yeah, and that's what we saw right here. This means a static member method can only access a class's static fields. The last example I wanted to show you was the different objects all access the exact same static field. And so we can see this by creating multiple instances of the same class, in this case my class. I'll call this MC2. And what I'm going to do is, we already conveniently have these print methods. So what I'm going to do is, well, I'll go ahead and just use a standard system.out.println, just to show you, right? Nothing funky is going on behind the scenes. System.out.println, and I'm going to print MC dot, we want the static variable, my static var. And then I'm going to use the other instance, MC2, to print the same thing. And not surprisingly, it's going to print the exact same value both times, 5 and 5. But to throw a loop, I'm going to change the value of the static variable in one instance and see if that change can be seen in the other instance. If it can, then it's clear that they share the same exact variable. So I'm going to say mc.myStaticVar, and this time I'm going to set it equal to, let's say 32. And if this holds true, then when I say mc2.myStaticVar, the value should be 32. We'll go ahead and run it. And you can see this is the case. 5, we changed the value to 32, and even though it was in a different instance where we changed the value, you can see that that change was seen in the second instance. And the real reason being is because you have to remember that static variables are tied to the class name itself. So really what I should be doing here is saying my class.myStaticVar. And what this means is each instance is sharing the same exact static variable. All right, enough of static for now. We're going to move on to memory regions. So your program's memory, and so recall that memory is this volatile area where your program is running once you've ran it, right? So if you think about any normal application you run, whether it's, I don't know, if you listen to music like Spotify, or you open up a browser, for example, Google Chrome or Safari or something like that, those are all running in something called memory, more specifically RAM. And we've previously talked about this in other lectures. So if you can imagine, all of your computer's memory is sectioned off where each program running or application is going to get a certain chunk of it. And of that chunk, your program is going to break it up into 4 different regions. Or I guess I suppose that there's 3 regions, where one of the regions is broken into 2 subregions. And so we'll go ahead and go into those 4 regions. There's the code region, which is under the main region called method area. And this is a region where your program's instructions are stored, as well as class information and things of that nature. There's the static memory region, which should not be new to you guys. We've just recently talked about it. That's also in the method area region. And so yeah, this is the region where static fields are allocated. The name static comes from these variables not changing, so static means to not change. They're allocated only once for the duration of the program, and their addresses are basically stay the same throughout the execution of your entire program. There's a region called the stack, and this region is where a method's local variables are allocated during a method call. A method call basically adds these local variables onto the stack, and a return statement will remove them. We'll go into more detail about what's going on with the stack later. And then there's the heap. The heap is a region where that new operator that we use allocates memory for objects. The heap also contains non-static variables that are class-wide in scope. So I have a picture to just help view this, because I can understand words can be somewhat hard to picture. But if you imagine, this entire box right here is the memory allocated for your specific program. And inside of your program's memory, you've broken it into 3 different sections. You have the method area, the heap, and the stack. Now the method area is broken into 2 smaller subregions, the code subregion and the static memory subregion. And so what I have in these different regions are a little more descriptive of what those regions are holding. So if we look at the code region, it's talking about class information. So for example, your program might have many different classes. And so what this is talking about is, a class name. Does that class inherit from other classes? Does it implement any interfaces? Things of that nature. It also includes the non-static method instructions. And so really, if we look at this code region, what is it? Well, if you remember, I talked about making an object, right, used a class as a blueprint. This code region right here is the blueprint for making these objects. It's what your program will refer to when trying to execute any of those types of instructions. The static memory holds static variables and static method information. This is why static can work so differently from non-static. It's because it has its own separate region where when your program compiles, it will go through all of the different classes that you have, find all the static variables, and put them, as well as static method, the instructions, and put them into this static memory region. It does the same for the code region as well, of course. So if we look at the heap region, there's the class-wide non-static variables. As well as object memory. Now, what do I mean when I say object memory? Well, if you recall, when I talked about what a reference type was, it was an address that pointed to some location in memory that held all of the information for a particular object. That's what I'm talking. That's where this memory exists, in a place called the heap. And so what happens is this new operator, it's going to go to the code section and figure out, okay, how do I create this type of object? How much memory is it going to need? It goes to the heap. It allocates that block of memory that that object might need on the heap. And then it returns the address to that memory. And then there's the stack. So the stack is your local non-static variables, basically scoped to methods. So all of your methods, every time you declare, initialize and declare a variable inside of a method, that variable goes onto the stack. And when you leave that method, that variable leaves the stack. That's why if you create a variable inside of a method, you can't access that variable in a different method. So I've prepared for you just a small little example. So we've got class foo. Foo, you can see, has a static variable called x of type int, and a non-static variable called y of type int equal to 7. There is a static printx method and a non-static printY method. The non-static printY method allocates or creates a z variable. That is actually a mistake. It should be printing z here. I'll fix that. Then I have a main class here. And this main class just has the main method. It allocates or creates a foo variable called myFooVar, and then calls the printY. So to translate this into what's going into the different memory regions, so if we look back, we'll start with the code, class information. So what's going to be in this code section, as well as non-static method instructions. There's going to be the fact that you have a class and it's called foo. That will go into the code region. Foo has a non-static method called printY. So the instructions for printY basically create z by finding whatever the value of y might be, and then print, this should be z. These instructions get saved in the code region. I also have a class main, and that will get saved into the code region. Note that this variable y is not getting saved in the code region, as well as, or the fact that a variable y exists will get saved in the code region, but the actual variable itself will not get saved in the code region. The static methods are also not getting saved into the code region. The static variable and the static methods, printx, and in this case main, are going to get saved in the static memory subregion of method area. And now if we follow along, right, we've got this int y equals 7. So when I have created this foo variable, you'll notice it's local to the scope of a method. So this variable name is going to reside in the stack, and its value is an address. But if you remember, all objects exist on the heap. So while the address exists in the stack, the object's memory for this foo object's memory will exist inside of the heap. So object's memory exists here, but the variable name and the value associated with it as an address will exist in the stack. And once I've created this variable, you'll notice that a y variable inside of the foo object gets created. This y variable is class-wide in scope and non-static. And so if we look at the print y method, when this z variable gets created, it actually gets put onto the stack. And it's a primitive type, so the actual value is the value of z, which is in this case the value of y, which in our case is 7. And that gets put onto the stack. And then once the print y method is done doing what it's supposed to be doing, the z method gets removed from the stack. I know I said previously that it takes a return statement, but if you notice the return type is void, which returns nothing, and so it's just kind of like an implicit return statement. All right, let's see. I think that's it for memory regions. We'll go ahead and look at garbage collection. So programs only have a finite amount of memory available to them, which makes sense, right? You can't just have an infinite number of programs open. Your computer's memory, your computer would eventually crash. Only a certain amount of memory is allocated for your particular program. And so what this means is you can only, your program can only be so big. You can only create so many objects and so many variables before you've exceeded the amount of memory that you're allowed to have. I suppose an analogy might be, right, you're given a cardboard box to pack up things as you move out of your dorms. You can only fit so many things into the cardboard box before it overflows. I think this concept can be applied in many places. And so because of this, memory management is important. Objects that are allocated on the heap take up a lot of memory. And so it's important that we get rid of objects when we're no longer using them. And this is the purpose of the garbage collection. It does this memory management for us. It will, once you've created an object and you've used an object and you're done using that object, you don't need to be the one to worry about, okay, well, let me go into memory, find where this object exists, where its memory is allocated, and get rid of it. Java conveniently does this for you. Other languages aren't so nice to you. For example, C or C++ don't have garbage collection, and what that means is every time you create, every time you allocate memory inside of C or C++, you must deallocate it, you must free it up. You'll learn more about all that fun stuff in later courses when you suffer under C and C++. And so how does garbage collection do this? Well, the true answer is quite complicated. And it's out of the scope of this class. But we can discuss a more simplified and abstract version of the real answer. And that is the JVM keeps a count, known as a reference count, to all of the reference variables that are currently referring to an object. So, and if that reference count hits 0 at some point, then that object is considered an unreachable object, and it is then marked for garbage collection. So you can imagine, right, you create a variable that's an object, and once there's nothing referencing that object anymore, it gets garbage collected. We can look at this inside of the IDE here. So if you look, I've created two objects. One is called MC and the other is called MC2. Now, we do some stuff with these variables, and if at some point I say, MC equals null, MC is no longer referring to the area of memory created by this new myClass call. And so since that reference count will hit 0, that memory is going to get garbage collected. Now in this case it's not a huge deal, right, because our program ends directly after this, so it's not a big deal. But if you had a more robust, fleshed out application, this starts to become a kind of a bigger deal. And so, as you might have noticed, this addresses that while yes, you are not the one who is physically going into memory, right, and deallocating it and all of that nonsense, you do have to worry about maintaining a reference or not to certain objects in memory. Oh, and I forgot to mention with the memory regions, this is all more complex in reality as well. This is just a more higher level abstract way of looking at things. And I think that's it for this lecture.